And as we were talking about last time, these are not as strong as a covalent bond. That's why they're called non-covalent. Nevertheless, they're strong enough to influence biological processes. And we were talking about ion pairs. Positive charge attracts a negative charge. You've got sort of the Coulomb's law relationship describing the strength of the interaction. Q1 and Q2 are charges, so the more highly charged something, the stronger the interaction is going to be. But these sort of epsilon terms in the denominator are important. I guess I'll just mention briefly radius. The closer they are together, the stronger the interaction will be. Sometimes people will say that this interaction falls off as 1 over r, which indicates that the further away you get, the weaker the interaction is. There are some types of interactions that fall off more quickly than that, and we'll talk about those. But let's talk about what this dielectric constant means. This is important because it describes the ability of the space between the two charges to respond to and adjust to the electric field between the two charges. And you can see based on this equation that if our dielectric constant is high, the energy of interaction between charges is going to be lower. And that is because the whatever is between the two charges is going to adjust itself so as to oppose the electric field between the two charges, and so the two charges won't feel each other as strongly. So this concept of dielectric constant is important. So I thought I'd give you a few values so you can see sort of how they vary. Very nonpolar solvent N-hexane has a dielectric constant of 2, meaning it's 2 times as responsive to an electric field as a vacuum is, but still not a huge amount. If you start to increase solvent polarity a little bit, you can increase the dielectric constant. So chloroform has a dielectric constant of 5. And you can just sort of go up the list. Dichloromethane has a dielectric constant of 9, but we're still sort of pretty low. If you get to an alcohol, suddenly you jump up quite a bit. So ethanol has a dielectric constant of 25. DMSO has a dielectric constant of 47, and of course water has a dielectric constant of 78. So this gives you a sense for in what contexts ion pairs are going to be significant versus insignificant. And this is why, for example, you can dissolve salt in water but not hexane. In hexane, the space between the two charges isn't enough, or rather the identity of the molecules that would surround the individual ions are such that the ions still feel each other quite strongly, whereas that's not the case in water. So this is just a good idea to keep in mind, that sort of nonpolar solvents have a dielectric constant that's closer to that of a vacuum versus water, which has a dielectric constant of 78. And this is a good time to point out strength of interactions. Strength is not an absolute term. It's always relative to what? So, as I was, I think, saying last time, this is why people will come out of Gen Chem thinking that ionic bonds are really, really strong, and then they'll get to OChem and we'll tell them there is no such thing as an ionic bond, and in fact, they're very weak. Well, who's right? Well, both of us are. The people coming out of Gen Chem are probably thinking of ions relative to being separated infinitely in a vacuum, whereas organic chemists and biochemists are thinking, well, relative to being surrounded by water, no big deal, right? Okay, questions about that? So there are solvents in which ion pairs can be important, like in inorganic solvents. I'm sorry, in regular organic solvents, and there are other solvents where ion pairs are less important. If you want to dissolve something, a salt, DMS, but you need organics to dissolve as well, DMSO is a decent solvent for that. It's polar but non-protic, and so it's actually used for a lot of substitution SN2 type reactions. So let me give you a few examples of ion pairs. Sodium acetate, you can dissolve that readily in water. The ion pair itself is not as stable as having the individual ions solvated by water. So what do we mean solvated by water? Well, we mean that you have a cage of water molecules surrounding both. In the case of the cation, you would have the sort of electron-rich part of the water molecule oriented towards the cation, and this would be surrounding the molecule in 3 dimensions. And then in the case of the acetate anion, you would have water molecules orienting themselves so that the electron poor part of the water molecule is near the acetate ion, and so on. And individually, the interactions between the solvent and the ion here, the anion here and the cation here, make up for the interaction between anion and cation that you had when they were closely associated together. I guess this now we're talking about, now that we're thinking about solvated ions, we're no longer talking about ion pairs, but rather Ion-Dipole interactions, right? Because each of the water molecules has a dipole that puts a partial negative charge on the oxygen and a partial positive charge on the hydrogen. Okay, so your real question as to whether something can dissolve in a solvent is, do the interactions the molecule has in the solvent overwhelm and pay for all of the interactions you're losing when you dissolve something? A biological example of a place, well, there are some polymers where if you have enough negative charges close together, you can increase the strength of ion pairs. So what I'm going to draw for you now is a polymer that's sort of based on sodium acetate. It's called sodium polyacrylate. This is in diapers. It's super absorbent material. If you ever get a chance to do a chemistry magic show, one of the fun tricks to do is, I don't know if it's fun for the kids, is to have water in a couple of cups, and one of them has sodium polyacrylate, and you pretend to dump the water on them, but you've already absorbed it into the sodium polyacrylate. It's not actually that funny, but what I mean here is that the fact that you have all of these ions close together makes the individual ion pairs more stable, and so there's a substantial amount of sodium that's near the carboxylates in this polymer. But the fact that you've got ion pairs here is one of the reasons why the polymer does such a good job of absorbing water molecules, because they can associate with and surround the negative charges. Classic example of a polyanion where ion pairs are important is in nucleic acids. So as you know, the sugar phosphate backbone of a nucleic acid is heavily negatively charged. What am I struggling with here? So here would be the base, whatever it is. and so on. You have these negative charges in the backbone of the nucleic acid, and they are often associated with counter ions, and especially with even ATP, but in DNA and RNA as well. Frequently you'll have magnesium as a counter ion because it can interact with multiple oxygens to stabilize the negative charge. So there are situations in water where ion pairs can be important. One of those is when you have a lot of negative charges in close proximity, so that you need some positive charges nearby to balance them out. Another situation in which ion pairs can be important is in proteins. So amino acid side chains, some of them are charged at physiological pH. So the amino acid lysine has the following side chain. Here's the beta carbon, gamma, delta, epsilon, and then there's an amino group which is protonated at physiological pH. The pKa of that group is, I always forget, so I'm not even going to tell you. It's something like 10. But it's always it's generally positively charged at physiological pH. There's another side chain that looks similar to lysine, only, let's see, beta, gamma, delta, nitrogen. And it's also positively charged, but the positive charge is sort of delocalized onto these three nitrogens instead of being localized on an amino group. This type of group happens to be called ammonium. Sometimes when people talk about lysine, they'll talk about the epsilon amino or ammonium group with lysine. For arginine, the protonated form is called guanidinium. I'm not sure if I spelled that right. And these positively charged side chains can interact with the negatively charged side chains. Aspartic acid or aspartate has a carboxylic acid that's negatively charged at physiological pH, and then glutamate, which is just one carbon longer, also has a negative charge at physiological pH. So the question is, in a protein, could you have a favorable interaction between the negatively charged oxygen of the carboxylic acid and the positively charged side chain of lysine or arginine? And the answer is, it depends, which is not very happy, but it honestly depends on location. So we're going to pretend that a protein is this large blob, okay? And we're going to pretend that we have a positively charged group here and a negatively charged group here. Now, remember what we know about whether there's an interaction between two charges and how strong it is. That's going to depend on a couple of things. It's going to depend on the distance between the two charges, and it's going to depend on the dielectric constant of the medium, and it's going to depend on the ability of the solvent to surround individual ions and interact with them. So on the protein surface, it seems likely that, and we'll represent water molecules interacting with these charges as these sort of blue circles. I may draw sort of one water molecule in there to remind you what we're talking about. But on the surface of a protein, these charged groups might be surrounded by water anyway, and so there might not be a strong interaction between the two of them. Remember, interaction strength is always relative to what? So relative, for the two ions to be interacting directly, they need to be close together, right? And then we're thinking about that relative to being separated, but not in a vacuum, being surrounded by water molecules. And in many cases, the difference in free energy between those two situations is pretty small. So in general, salt bridges these are sometimes called salt bridges instead of ion pairs. We use those terms interchangeably. Surface salt bridges are often quite weak because they're not any more favorable than just having the individual ions surrounded by water. However, there is evidence that inside a protein, salt bridges can be quite strong. So if you know anything about protein folding, you know that the surface of the protein tends to have polar groups on it, whereas the interior tends to be nonpolar. And in fact, we'll talk about how the hydrophobic effect leads to a protein burying its nonpolar groups so that they're not exposed to water. But what do we know about nonpolar groups? Well, let's go back to our list of dielectric constants. If you get less polar, your dielectric constant goes down and the strength of your interaction goes up. So you might predict that salt bridges in the interior of a protein might be quite strong, and that in fact is often the case. One example of an interior of a protein that you might think about would be if this protein had some sort of binding pocket, which these are often lined with nonpolar residues. And so if you had a positively charged residue next to a negatively charged residue here, the interior is going to be much more like a nonpolar solvent with a low dielectric constant. And therefore, the interaction between the two charged residues, the salt bridge or ion pair interaction, can be much stronger. So context matters. All right. Anything more you want to say about that? Some of the research in my lab has been related to understanding how interactions between charged residues can depend on the immediate environment around the charged residues. And we've learned that the environment matters quite a bit. I guess we could talk briefly about how you measure the strength of these interactions experimentally. That's done by something called mutagenesis. And all this means is if we think that two amino acids interact with each other, we want to measure the strength of the interaction, we get rid of the interaction by mutating one amino acid, swapping it out for another that doesn't have the positive charge. Okay? So as an example, suppose, again, we have our protein and we're interested in knowing whether having this positively charged side chain next to a negatively charged side chain matters. What we can do, this is the amino acid lysine, let's say this is the amino acid glutamate. What we can do is replace lysine with the amino acid alanine. And that amino acid alanine is much shorter and has just a methyl group, no charge, right? Okay, so you could measure, say, and then you'd need some way to measure how stable the protein is here and how stable it is once you replace the positive charge with the alanine, which doesn't have a charge. So let's suppose we measure folding free energy for the first protein, and we measure folding free energy for the second protein. If we make that comparison, a question we could ask is, do we now know how much that salt bridge is worth? And the answer is not quite, because when we changed lysine to alanine, we didn't just get rid of the salt bridge, we also swapped out an amino acid that used to be lysine for something that's different. So we have to account for the impact of that change without the possibility of the salt bridge being there. In other words, the protein already exists, that lysine might be a particularly good amino acid at this position, and so when we mutate it out, we may see mostly that effect, and we may not see what the effect of having the salt bridge is. And so what we do is we repeat that experiment with another variant in which we still have the lysine, but now we've replaced the glutamate with alanine. And then we change lysine to alanine. And then we'll call this delta G3 and this delta G4. This change in free energy tells us what the lysine to alanine mutation does without the salt bridge interaction present. And then this difference in free energy tells us what the lysine to alanine mutation does with the salt bridge present. So if you subtract this change in free energy from subtract this change in free energy from this change in free energy, we will have isolated out the effect of having the salt bridge present. Okay. This gets ridiculous, right? With all of the deltas, we start to look like we're trying to start some sorority or fraternity or something like that. But this will tell you the strength of the interaction that you're interested in. I've been sloppy with signs here. Technically, if we wanted a number that reflected the favorability of a salt bridge interaction, we would start here, go to there, start here, go to there, and then subtract those double delta G's. But in any case, this process of trying to figure out how much an interaction is worth is called double mutant cycle analysis. You have, oops, didn't want that. You've got to have 4 different variants, every possible combination of the original amino acids versus alanine, and when you have those 4 variants, you can calculate what the interaction between the two is. I get on my grad students' cases when they can't explain that well, and I'm not sure I did that great of a job just there. So, any questions you want to ask?
What do we measure the delta G with? Like, what kind of machine?
Yeah, how would you measure folding free energy? Or you could also, it could be some other readout. Suppose this protein has a binding partner, and maybe you could measure the strength of binding. There's a whole host of techniques to analyze protein structure. Some proteins have amino acids in them that are fluorescent, and that fluorescence changes whether the protein's folded or not. So you could watch fluorescence and then turn up the temperature and watch the protein unfold, or you could add some kind of chemical denaturant to make the protein unfold, and you could fit the data to equations that give you the folding free energy. All right. Others. All right, well, we kind of beat that one to death. We've already sort of talked about ion-dipole interactions when we were thinking about how to dissolve an ion pair. And this is where non-covalent interactions get a little bit silly, because basically any type of interaction you can imagine between a full or partial positive charge and a full or partial negative charge, you got it. So in the case of ion-dipole, you have an ion interacting with a dipole, which is because of the electronegativity of some atoms versus others. Dipoles are vector quantities. They have magnitude and direction. So the math for calculating the energy of a ion-dipole interaction gets a little confusing. You need to know not only the distance between the charge and the dipole, but also the angle. So I hate this. I'm not going to ask you to memorize it or be aware of it, but I just want you to see the form of an equation. This is a dipole. A dipole has a positively charged end and a negatively charged end. And here is an ion. We'll call that Q2. So you draw a line from the charge, the ion, to the middle point of the dipole, and then you measure this angle. How you can do this, I don't actually know, but theoretically, the strength of that interaction should be equal to mu, which is a new quantity which we don't care about, called the dipole moment, but it tells you how strong the dipole is. It equals the charge at one end times the length of the dipole. So you multiply that by charge 2, and then you have cosine of that angle. And then you have in the denominator 4 pi dielectric constant, permittivity of a vacuum, and now r squared. So comparing that to the ion pair equation, where it was just r in the denominator, we could see that ion-dipole interactions decrease in strength faster with increasing distance or increasing r versus ion-ion interactions. That's terrible penmanship. But do you see how that's the case? If r squared's in the denominator, suppose that we go from this distance r to twice this distance. The energy of the interaction, instead of decreasing by half, is going to decrease by a factor of 4, right? Because it's r squared. In contrast, for the ion pair interactions, if we increase the distance, if we double the distance between two ions, the energy goes down by half. Okay? All right. A classic I guess while we're dealing with this, we just as well deal with dipole-dipole interactions as well. And in both of these categories, ion-dipole and dipole-dipole, you can find something called hydrogen bonding. So as an example, here we have the electron poor end of the water molecule dipole closely interacting with the negatively charged oxygens of the acetate anion. We would call that a hydrogen bond. But it's just a dipole-ion interaction. Similarly, if two water molecules were interacting with each other, we would call that a hydrogen bond, but it would be a dipole-dipole interaction. Oops. Where the dipoles are lining up sort of in this direction. Because the dipole is a vector quantity, you might expect hydrogen bonds to depend on the angle between the two dipoles, and they do, but the dependence is not really strong. I will also say that dipole-dipole interactions fall off with 1 over the radius cubed. So these will decrease even faster than ion-dipole interactions. All right, yeah?
Could you, explain the interactions between ion-dipole one more time? I guess I'm just confused how that's different than the ion pair.
How is it different than an ion pair? In an ion pair, you have a full charge on one molecule interacting with a full charge on the other. For ion-dipole, you have an ion interacting with something that's not charged but has partial charges on one part of the molecule.
So those are like two separate things.
Yes, I'm sorry. These are not ion pairs. These are solvated ions, and I guess we could just delete that one.
Okay, it's fine. I was just.
Yeah. Yeah, sorry about that. I could see how that was confusing. Okay, others? Yeah.
So I know that water also has hydrogen bonding.
Yes.
So, and hydrogen bonding should be stronger than dipole-dipole. Does that matter in that case?
So hydrogen bonding is a kind of dipole-dipole interaction, and because hydrogen is small, the two dipoles can approach each other closely, and so yes, hydrogen bonding does tend to be stronger than a regular dipole-dipole interaction. I just don't put it in a separate group because physically it comes from the same thing. Yeah. There are equations about dipole-dipole interactions, which I don't think I have written down here, but I've not actually thought about them since I wrote them down here, so I don't think it's worth you guys knowing. But if you ever need to know distance dependence and angle dependence for a dipole-dipole interaction, the math is there and you can go look at it. So hydrogen bonding is a special kind of dipole-dipole interaction. And yes, go ahead.
Can we give another instance where we have a dipole without hydrogen bonding?
Sure. So acetone has a dipole. And so you could imagine individual acetone molecules orienting themselves like this. It's probably not very strong, probably short-lived, but yeah. Okay, so hydrogen bonding is a class of dipole-dipole interactions or ion-dipole interactions. And we have a special kind of language talking about these, and it's kind of a problem. So you've got a donor that's bonded to a hydrogen. Usually the donor is electronegative. So the hydrogen is electron poor, such that there's a partial minus on the donor and a partial positive on the hydrogen. And then you have an acceptor, and the acceptor is also usually electronegative. Usually it has lone pairs on a heteroatom. Usually it has a partial negative charge. And usually it approaches the hydrogen in such a way as to engage in the dipole-dipole interaction. So I'm drawing the dipole for the donor, and then here's the dipole for the acceptor. Okay? So the reason this is problematic is because these acceptors are usually nucleophiles, which are electron donors. So it's easy to get just totally mixed up on this. When someone says a hydrogen bond donor, that means the thing that's contributing the hydrogen to the hydrogen bond. A hydrogen bond acceptor is the thing that's receiving the hydrogen bond. So you'll have to get used to that. I don't particularly like talking about hydrogen bond donors versus acceptors, but there are some times where that's convenient. So let's give you just a few examples of hydrogen bonds. Of course, we've talked about water. Here's HF, which is a particularly nasty thing. And then here's a water molecule. And you can have the dipole for the water molecule lined up with the dipole of HF such that there's a favorable interaction. You can draw it that way, or if you want, you can just put partial positive charge on the hydrogen and partial negative on the oxygen, or you can just draw the dotted line. Everybody sort of understands all of those ways of talking about hydrogen bonding. Now, the dipole-dipole interaction gets stronger at closer distances, and so that's when hydrogen bonds start to get particularly strong. In fact, you can almost think of a hydrogen bond this way. Why not? So here's HF. Let's draw the sigma star for that molecule. That would have a node in between hydrogen and fluorine. It would have a lobe here and a lobe there, and then another lobe there on the hydrogen, and we could just fill in the phases to show the change. So that's the empty sigma star. And then here we have water. And we've talked about water before as having a P-rich lone pair and an S-rich lone pair. It's not actually going to matter which is which because all of that gets mixed up when a water molecule isn't on its own anyway. But you could imagine the lone pair on this water molecule getting close enough that maybe it's partially dumping its electron density into the sigma star of the hydrogen bond donor. And in that case, you would expect the hydrogen to sort of be shared, perhaps not equally, but somewhat between the two atoms. And there are some cases where hydrogen bonds are said to have partial covalent character. These can range, if they are very strong, these can range from 15 to 40 kilocalories per mole. That's, maybe part of a covalent bond in terms of strength. Moderate would tend to be 5 to 10 kilocalories per mole, and weak would be sort of 0 to 4. And all these strengths are always relative to what? So as with salt bridges, you would expect hydrogen bonds to be stronger in nonpolar environments. And you would expect them to not be quite as important if the solvent is also capable of hydrogen bonding. So the same thing, imagine having two molecules of HF interacting with each other via this kind of hydrogen bond. We could ask, what's the strength of that hydrogen bond between these two versus this? And the answer is probably not a huge difference. And so that's why you have to be careful in thinking about hydrogen bonds in protein and nucleic acid structures, because you'd be tempted to say, oh, that hydrogen bond there is important. Well, important relative to what? If it's a protein, let's just imagine this situation. Here's our protein, and here is your hydrogen bond donor, and here is a hydrogen bond acceptor, and you want to know how much is it worth. You have to consider maybe you have a crystal structure so you know that they're hydrogen bonding with each other, but you have to consider what your alternative is. If you're comparing it to the fully unfolded protein, maybe now the hydrogen bond donor is getting an acceptor from water, and the acceptor is getting a hydrogen bond donor from water. So who's to say whether these two hydrogen bonds with water are any stronger than the two hydrogen bonding with themselves? Should we say that again? If you're looking at a protein and you want to know, is this hydrogen bond important for how stable the protein is? when you're asking about protein stability, the question you're asking is, what is the free energy difference between the folded versus the unfolded conformation? And if your donor and acceptor are hydrogen bound to each other in the folded conformation and are each hydrogen bound to water in the unfolded conformation, then probably that hydrogen bond doesn't make a huge difference. In contrast, hydrogen bonds that are buried can be much stronger. And there's a report out of Jeff Kelly's lab from, I think, 2008 that demonstrates this in pretty good detail. Yeah.
By hydrogen bonds that are buried, you mean that
So if inside the protein somewhere you had a donor, oops, I got it wrong, see? If you had a donor hydrogen bonding with an acceptor inside a protein, this is probably a stronger, more important hydrogen bond than this one on the surface.
okay, which is much similar to what we discussed earlier with
Exactly, very similar to what we discussed earlier with the salt bridges. Yep.
So another question will be, because we just saw hydrogen bonded between hydrogen and fluorine.
Yeah.
But I always wonder if hydrogen and fluorine can hydrogen bond with each other. Why can't hydrogen and chlorine hydrogen bond with each other? Will it be because of the size?
Yeah, it's a great question. So, what about this kind of hydrogen bond? How strong is that? And it would depend probably on the relative electronegativities of fluorine versus chlorine. So you'd predict based on that it's a weaker interaction. I think size is probably important. And sometimes you can gauge propensity for, you can gauge, let's see, acceptor ability by thinking about the conjugate acid of the receptor, or of the acceptor, sorry, I don't know what we're talking about here. So as an example, the pKa of HF, if I want to know how strong an interaction is involving fluorine, the pKa of HF is about 4. The pKa of HCl is like -9, which tells you that chlorine is much less nucleophilic than fluorine, at least is in certain solvents, but so you'd predict it would be a not quite as good electron donor, not quite as good a hydrogen bond acceptor. Yeah, so thankfully everything you've learned about nucleophilicity and basicity, how reactive is this lone pair of electrons, that translates directly into hydrogen bonding. It's thought that hydrogen bonds get stronger when they're between groups that whose conjugate acids have similar pKa's. Let's see. So there are other ways you can measure the strength of a hydrogen bond. This example comes out of Sam Gellman's group in the early 90s. This is actually what got Sam tenure at the University of Wisconsin, these early hydrogen bond studies. He used infrared spectroscopy to tease out some things about hydrogen bond strength, and he made this model system in which only one hydrogen bond was possible. So I don't know why they drew it this way either, sorry. But they could tell based on the NH stretch in the IR spectrum whether this hydrogen was involved in a hydrogen bond with this carbonyl group or whether it wasn't. And they learned that in chloroform, nonpolar solvent, right? If this were in water, you get an entirely different result. The enthalpy of the interaction was probably minus 1.6 kilocalories per mole, and then the entropy was like minus 6 calories per mole per Kelvin, and you could calculate delta G as a result. You could calculate delta G because of that, and of course it would depend on the temperature, but assume it's about room temperature, and you're looking at anywhere between 2 and 3 kilocalories per mole, favorable to have the hydrogen bond versus the open chain conformation. Now again, that's in chloroform, so if you change the solvent, you'd change these numbers entirely. Okay. We talked about impact of solvent. I think that's probably all we want to do there. So, I mean, do I? I'm sorry, I'm trying to figure out how much I want to beat this horse. Why would you beat a horse? That's horrible. Okay, so as you know, alpha helices in proteins have hydrogen bonds between carbonyl oxygens and amide nitrogens. So here is a helix. It's a terribly drawn helix. Here is a carbonyl oxygen. This is the N terminus of the peptide. This is the C terminus. You have, oops. Hydrogen bonds from one turn of the helix to the other, and these are thought to stabilize the helix. And the question is, by how much? So I'm sorry, I didn't. Oh no! Here's the NH group. So in early work from Peter Schultz's lab, and I'll write down the reference later, but I'll show you what they did. They took a single hydrogen bond in a helix, and they got rid of it by making the ester version of the peptide at that position instead of the acid. So there's a couple of things that happen when you go from amide to ester. First, you lose this hydrogen bond between this amide nitrogen and this carbonyl oxygen. You also generate some repulsion between electronegative oxygens. And then finally, you change the strength of the hydrogen bond here because you've got to be worried about whether amides versus esters are better hydrogen bond donors. And we'll talk next time about how they're poorer. Anyway, stay tuned. We'll have just a bit more to say about hydrogen bonds, and then we'll move on to other things.